Muy buenos días a todos. Voy a presentar brevemente al doctor Mauro Epifani. El doctor Epifani obtuvo su doctorado en física en la Universidad de Lecce, en Italia, en el año 2000, y desde 2001 trabaja como investigador permanente o definitivo en el Instituto de Microelectrónica y Microsistemas del Consejo Nacional de Investigaciones de Italia. Sus intereses científicos se centran en el desarrollo de métodos de síntesis química en fase líquida en materiales avanzados para aplicaciones ambientales, sensores químicos de gases para la obtención y para la descontaminación de agua. Ha publicado alrededor de 80 artículos en revistas indizadas, su índice H es 28, y ha presentado alrededor de 30 pláticas invitadas en congresos internacionales. Entonces, el día de hoy nos va a hablar sobre nanocristales de óxidos metálicos coloidales, su síntesis por métodos químicos en fase líquida y algunas aplicaciones ambientales. Entonces, le damos la cordial bienvenida a Mauro, que habla muy bien español, pero nos va a hablar en inglés el día de hoy porque por cuestiones de terminología química y demás, me dice que se le complica dar su plática en español. Nos hablará en inglés. Eventualmente, si quieren hacer alguna pregunta en español, yo creo que también sí podrías contestar. Bueno, pues muy bienvenido, Mauro.
Muchas gracias. Muchas gracias, Rodolfo, por esta introducción y también por invitarme aquí. Ya intentamos algunas veces de hacer algo juntos y algún proyecto. No es tan fácil, pero con esta visita, como puedo decir, ya estamos empezando a hacer algunos enlaces más sólidos con muchas otras personas del departamento y creo que hay posibilidad de hacer muchos otros trabajos juntos en el futuro. Y también quisiera agradecer a la UNAM por el soporte de esta visita, claro. Y creo que sí, es mejor si cambio a inglés para la presentación, ¿no? Porque me gusta mucho hablar español, pero creo que para ustedes sería una lástima que me quede cada 3 palabras para preguntar cómo se dice en español y cómo se dice este. Así vamos a inglés, aunque no me guste muchísimo. Quisiera hacer toda la presentación en español, pero espero la próxima vez. So, we are a part of the Institute for Microelectronics and Microsystems, which is a part of the National Council of Researchers in Italy. The National Council of Researchers is a very big institute which is carrying out research activities in practice in every field of knowledge, starting from human sciences to physics, chemistry, engineering, and technology. So we are just a part of the National Council of Researchers. And after the Reformation process, which occurred more or less 15 years ago, many of these institutes were joined together to form some kind of micro institutes. So this IMM, Microelectronics and Microsystems, is composed in practice by 6 institutes. We are located in Lecce, which is in the southeast, that's in the Greek part of Italy, looking to Greece. Overall, in the institute, there are many research topics. We are organized our activities more or less in application areas, so functional materials and devices, MEMS, MOAMs for instance, chemical, physical, and biological sensors, which was one of the core activity of our institute before the formation of these macro institutes. Then we have a department devoted to photonics, with activities on optoelectronics, energy conversion devices, and so on. And related to these application areas, we have technological areas, which provide the material and technology and device support to these application areas. So, in my specific case, I work in the technological area of synthesis of advanced materials for chemical, physical, and biological sensors. This was our initial activity in lecture before we were joined to the other institute, and this continues to be our core activity currently. But now we are trying more and more to integrate our activity with the other researchers throughout Italy belonging to our institute. So this is basically to say what is the origin of this synthesis of advanced materials in our institute, and how is it related to my own research field. So, for this reason, I will give a very short introduction concerning chemoresistive gas sensors and the interest for using nanomaterials for improving the performances of chemoresistive gas sensors, and how it is important to develop curiosity-driven approaches for synthesizing materials for chemoresistive sectors. Why? Because by developing these approaches, we can then develop some general principles which are useful for synthesizing and processing chemical precursors. And in this way, we can even go beyond sensing devices. Currently, we have some activities on water remediation, energy storage applications, and possibly even other possible applications. So, in chemoresistive solid-state gas sensors, what happens is that we have the substrate, an active material, and the gaseous molecules which interact with the surface of the active material. Electrons are depleted from the active material, and when a gaseous analyte is reacting with our sensor, these electrons are given back to the material. This means that we have a modulation of the charge current concentration. Or, shortly, we have a change of the current or of the resistance of the sensor when it is exposed to a given gas. Which means that, in principle, we can detect the presence of a given gas by simply following the change of the electrical current crossing the device when it is exposed to the gaseous analyte. More or less 30 years ago, there was an interesting work by Yamamoto in Japan which suggested that nanocrystalline materials could give rise to improved performances in gas sensors in terms of higher sensitivity, better selectivity, and longer stability. Very, very briefly, we can think that we have a larger grain. The charged depletion layer which is formed upon interaction of the sensor with oxygen is less important with respect to the whole grain than in the case we have smaller grains where the charged depletion layer is more important. So it is expected that we may have faster and larger relative resistance change in smaller grains. For this reason, an intensive research effort started since then, and still it is going on, for developing nanomaterials and for applying them to this kind of chemoresistive sensing devices. So, the first application we tried to develop was the synthesis of thin films, because the historical activity of the Institute was mainly focused onto the synthesis of thin films. So is it possible to prepare nanocrystalline thin films? If this suggestion that nanomaterials can improve the performances of chemoresistive gas sensors, then why not begin with the synthesis of nanocrystalline thin films? And from this point of view, chemical processes naturally provide nanocrystalline films, simply because there are many, many nucleation points in the film when you do the synthesis. So the mass transport of the material during the heat treatment process for crystallizing the material is limited to very small zones. Basically, this results in the creation of small grains. The advantages, which are suggested to use chemical processes, are also that we can design a suitable choice of the precursors, so obtaining cost-effective procedures, stable solutions, and simple procedures, by using simple and inexpensive equipment, by making films by spin coating, we just need a very, very small, like a box. If you do films by sputtering or thermal evaporation, you need enormous apparatus, which are also complicated to manage. We can easily introduce additives, dopants into the active layers. We can control the film morphology, and we can think to unify the synthetic approach, which means that the whole process can be thought to work like a coffee machine, where you just insert a different precursor, and at the end you get a different oxide. So you just establish the starting principle, and from then it is just necessary to change the chemical precursor. This, in principle, is an advantage of the chemical processes for making nanocrystalline films. Moreover, one further requirement was that we needed the development of processes compatible with silicon micromachine platforms, since the focus of our institute is to prepare micro devices to be integrated into more complex architectures. So these devices should be miniaturized in order to obtain low power consumption. They should be integrated in more complex architectures. And we need low cost in order to think to mass production of many devices. So this was another requirement, which conducted us to think to the development of chemical processes. In our group, there was already an activity concerning the films, the synthesis of thin films and other materials by the Sol-Gel process. So the first idea was to use the Sol-Gel process to synthesize these thin film materials for gas sensors. I will just give very, very short basics about Sol-Gel processing, since it has become so much popular since many years. So basically, the precursor for Sol-Gel process in classical Sol-Gel science is an alkoxide, where a central metal atom is bonded to alkoxy group, like in titanium butoxide. When this alkoxide reacts with water, with hydrolysis, the formation of an OH group. Condensation of two OH groups from two hydrolyzed molecules leads to the formation of an oxide network, which is the advantage of using Sol-Gel process. We can easily deposit thin films, as I was saying before, by spin coating or deep coating. We've always been using spin coating. We can think to deposit onto complex shapes of the substrate. And again, in these additional dopants, we can chemically tailor the precursor. We can carry out many interesting chemical modifications of the structure of the precursor. And easy formation of the oxide network. Hydrolysis and condensation are something that are carried out very, very rapidly, even at room temperature. So we don't need, in principle, to carry out very complex reaction to get an oxide network. The most difficult thing is to carry out a heat treatment after the synthesis for crystallization of the film. But the Sol-Gel process seemed very much interesting as concerning the possibility of preparing thin films. But there was one very big problem with the use of alkoxides, which is the high cost of commercial alkoxides. This is a comparison in euro per gram between the price required, the cost required by using alkoxide for various elements, as compared with inorganic precursors like nitrates, chlorides, which are much more cheap. And they also have some other important advantages. For instance, the alkoxides are stable, they are moisture sensitive, you have to handle them into a glow box, and they are very pricey. But the inorganic precursors also have another disadvantage, which is that it is not easy to process some solutions to prepare thin films. We have problems of inhomogeneity, of adhesion to the film, to the substrate, and so both classes of precursors have some advantages and some disadvantages. So the idea was to develop some alternative precursors having better stability and lower price than alkoxides, like inorganic precursors, but good processability like alkoxides. So cheap and stable precursors given uniform and films with a good adhesion to the substrate. This will be the path line that we will be following in this first part of this presentation. The development of these alternative classes of precursors and how it is possible to use these precursors, which were initially designed for making thin films, for making colloidal oxide nanocrystals. In which way? By following some curiosity, some connection with the work that was initially completely far away from this work. But, stopping, considering this slide, we will go on in this way. So, if we have metal alkoxide that do not have particular disadvantages, like titanium, which can be, we can use them very easily. We will see an example at the end. But, if it is not convenient, we will see the development of some alternative precursors. First, metal chloroalkoxides. If they are not useful, when they are not advantageous, we develop another class of precursors, which are metal 2-ethyl hexanoate. When both these two classes are not useful, we will see how we can also use metal nitrates as a precursor, so simple inorganic precursors. So, let's start from the first class, the metal chloroalkoxides. In general, tin alkoxide is prepared by reacting, for instance, propyl alcohol with anhydrous tin tetrachloride in presence of an amine. What happens is the formation of a chloroalkoxide plus some precipitated byproducts. I'm not going into detail in formulas in chemistry since I don't want to be too much heavy about this point. We will see just some formula in the afterwards. I kept the chemical details as limited as possible, just not to be too boring. What is the problem with this procedure? Is that if we have a pure alkoxide, it is necessary to eliminate these chloro groups which are bonded to the central tin, for instance. And this purification procedure is very long, is expensive, so that the final tin alkoxide is extremely expensive. Also, I remember that once we bought some tin alkoxide for making some comparison, and it was extremely unstable. You just do one solution, you use it one day, it is very expensive. The day after there was some precipitation into the container, so it's not so much convenient. So the idea was to use the same procedure at the beginning. So some tin tetrachloride reacted with alcohol, we get our chloroalkoxide, and we do not carry out any purification. We just use directly this chloroalkoxide. We carry out our Sol-Gel process, we add water, and surprisingly, there was no precipitation. These solutions were extremely stable. So why people are in general trying to use alkoxide and not this other kind of precursor? For instance, because we have some residual chlorine, which could contaminate the final film. But we could detect that after the heat treatment of the thin films, there was no residual chlorine. So this class of precursor seemed extremely promising. And now let's see if really some thin films could be achieved with these chemicals. If you remember from a few slides ago, one of the possible advantages of using chemical processing is that you can use the process as a coffee machine, I would say. And this was the case. We had exactly the same procedure. Some metal chloride reacted with alcohol, some residual chlorine which stabilizes the precursor. We had some water, we don't have any precipitation. And in this way, we could prepare chloroalkoxide from tin, titanium, zirconium, vanadium, molybdenum, and so on. There are many possible elements which can be processed in this way. The synthesis is fast and easy. You don't even need to use a glow box. You have a stable solution, and easy chlorine elimination after treatment, or in some cases, after the spin coating of the film. even after spin coating, there was no more residual chlorine in many cases. So technically, it is very easy. After preparing the chloride oxide, we put some CdSe, which is a precursor which is useful for improving the wettability of the substrate from the solution. Some spin coating onto silicon dioxide or silicon nitride, drying on the films, and finally treatment. So it's extremely simple. The problem was, spin coating is always extremely simple. The problem was to develop a sufficiently advantageous precursor. And in principle, this chloride oxide were satisfying these requirements. Moreover, we didn't need to reduce moisture in the spinning or the following steps. With the oxide, what you have to do typically is to have your spin coater inside the bag. You flow some nitrogen or sarangol inside the bag in order to reduce the humidity, and then you can do the spin coating, but using some gloves, which is quite uncomfortable. When using this precursor, they are so stable that you carry out the spin coating in the atmosphere without using any other air control. Some examples. The process indeed proved to be extremely successful for making, for instance, tungsten oxide, tantalum oxide, indium oxide, vanadium oxide, and so on. This is a panoramic view of some spin films made also by other processes that we will see in the following. But you can see that in general the films are extremely uniform. They cover the whole substrate, and they could be processed, as we shall see at the end, by microelectronic procedure to prepare the final sensing devices. So, until now, the initial idea of using this modified precursor was successful and allowed us to prepare many different films of various materials. But there are some cases where chloride oxide are not useful. For instance, in the case of tin dioxide, which is a very important case, it was very unfortunate since after spin coating, this was the situation. This is the substrate, and this is a single drop of the solid. There was no deposition. The substrate was completely repelling the solution due to the chemical composition or the surface tension of the solution. It was impossible to have a deposition. It was a real problem since tin dioxide is the most typical oxide that is used in sensing devices. So just for this material, it was not possible to get uniform thin films. Not uniform. It was impossible to get a film. There was nothing on the substrate. For this reason, we were checking for the possibility of using other simple precursors to substitute chloride oxide when they do not work. I will skip to the details about the search of these precursors, but it was possible to find them in metal 2-ethyl hexanoates. This is the case of tin. We don't need to look in detail this part of the molecule. We just need to know that it is very cheap. It's non-toxic, it's air-stable, and the processing is extremely easy once again. We just dissolve some precursor in butanol, we have the surfactant, the CdSe that we have seen before, spin coating and treatment. So once again, even from this important material, it is not necessary to use alkoxides. We have another class of precursors, metal 2-ethyl hexanoates, which can be used for making thin films. They are very convenient. You can find them for many, many elements. They are cheap and they are stable. You can use them under air without any kind of control of the atmosphere. What is the result? It was very satisfying. You can see how uniform a thin film was obtained by using this precursor. It was nanocrystalline. We can easily see the tin dioxide rays composing the layer, and the crystallographic phase was the typical tetragonal for tin dioxide. But there is one more case when we cannot use chloride oxides, we cannot use ethyl hexanoate, like, for instance, another important oxide like indium. Why? You can buy the alkoxide, but it is really expensive. You cannot use it easily because it is very reactive. The ethyl hexanoate, same problem, it is very expensive. So the chloride oxide cannot be prepared. So how to solve in this case? Well, we use a simple indium nitrate, a simple inorganic precursor. So if you remember a few slides ago, there's the timeline of the development. Chloride oxide, ethyl hexanoate. We are to the third class of precursors which you use when you cannot use the other classes. And it is, again, very easy to prepare a solution. We dissolve in methanol with acetyl-acetone, which is a stabilizer, and it is useful because when we have our base for making that Sol-Gel process, there is no precipitation. It is important to avoid precipitation. You can dissolve a precipitate by adding some acid, but we have observed that in this case, making thin films from solutions prepared from precipitates is not so easy. They are not so uniform in general, and they do not have a very good adhesion to the substrate. So this procedure to prepare a modified indium oxide solution was useful for avoiding precipitation and for making a uniform film, which is also very porous. You can see the indium oxide nanocrystals inside the film structure. And once again, we have the typical cubic structure of indium oxide, its final crystallographic phase. Finally, there are some cases where you can use the metal alkoxides. In the case of titanium, you don't need to do any kind of chemical modification, anything. You just buy the commercial precursor, you carry out a typical chemical modification, and by spin coating, once again, they are very, very uniform thin films with a thickness of about 15 nanometers in this case, very clearly nanocrystalline, with a typical anatase crystallographic phase. Well, I do not go on with this parade of metal oxides. What we do with these materials, what we did with these materials, was to process our thin films by microelectronic procedures, by using photoresist technology. We could, at the end, prepare after various steps which are carried out by colleagues into the clean room. We finally have our devices where we have deposited some electrodes onto the top of the film, of the substrate, while onto the back we have deposited some heaters so that the substrate can be heated to a given temperature while being operated in presence of a gas. The typical size of these devices was 2 millimeters, or 2 millimeters. And after being mounted onto a support, we have our final sensing device. And did they work after all this development? Fortunately, the results were very much interesting. This is the detection of carbon monoxide by thin oxide thin films, the films that I have been showing a couple of slides ago, which were giving a very reproducible and stable signal at various operating temperature in presence of various carbon monoxide concentration. So we could get a complete calibration curve concerning the detection of carbon monoxide, the development of gas sensors for carbon monoxide by our devices, starting from the old idea, the early idea to use alternative precursor to metal alkoxides. Another example, hydrogen detection with titanium thin films, which showed similar results, very interesting signal, it's very over a broad range of operating temperature, over a broad range of hydrogen concentration. These are the calibration curves. It's not so interesting to show some dozens and dozens of results of gas sensing, just to show that the circle was closed from the very early conception of the precursor to the processing, device testing, and demonstration that the whole process could be closed. The whole circle, the whole loop could be closed. The problem was that still the responses that we were obtaining were not so high. This is because the preparation of thin film is a limitation to the porosity of the material that you are using. for this kind of application, gas sensor, it is important to have a porous material. If you have a thin film which is then deposited onto a substrate, most probably you will get a very, very low porosity, because the contact area between the substrate, between the device and the gas is just limited to the upper face of the film. You don't have any other contact. This is why it was necessary to prepare some other kind of morphology. And in that period, colloidal oxide nanocrystals, were being shown to be a very promising alternative to thin films. This is why we switched to colloidal metal oxide nanocrystals. So, if the core of the presentation is the synthesis and the application of metal oxide nanocrystals, why was I presenting this boring part about chloro, oxide, blah, 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 and so on? Because there is a cross connection between all these precursors, all these molecules that we have seen until now, and the synthesis of nanocrystals. How could we establish this connection? By following the curiosity. This is something that they are stressing more and more, because nowadays most probably most works are directly devoted to the application, and it seems that following some curiosity is not so useful. Actually, this is the core of our work, asking questions that are not expected, considered to be unuseful and so on. But this is a demonstration that making some strange question or developing some quite strange work can be the kind of precursor that is available for a given element. Then, for getting to the second part of the talk, we go to something that is apparently very, very far away. Cadmium selenide nanoparticles. Why is it important? During the course of this study, what we observed was that we could obtain the crystallization of amorphous cadmium selenide nanoparticles depending on the size of this nanoparticle. Smaller nanoparticles were more easily crystallized. You needed to heat them like at 150 degrees, for instance, yes, for 2 hours when they were 1.7 nanometers. While when they were much larger, something like 3.9 nanometers, we needed 190 degrees C for 3 hours. So the smaller the particles, the easier the crystallization. This can be seen in this schematic figure where our amorphous particles have a different starting energy, so that the smaller nanoparticles have some less stable configuration toward higher energies, and we need less energy to overcome this kinetic barrier going to the nanocrystal formation. But what was important was this conclusion. Smaller particles are in more favorable metastable condition. Cadmium selenide nanoparticles. What is the connection with our work about oxide? Because we simply wondered, is it possible to transfer these results to oxide systems? Because the results that were obtained were in no way related to the fact that we were dealing with cadmium selenide. It seems that we were dealing with some general principle. So if we have this initial principle, smaller particles require much less energy to be crystallized. Then if we prepare small amorphous oxide, no more cadmium selenide, oxide particles, and we slightly heat them while keeping them separated in order to limit the growth. Can we prepare oxide nanocrystals by using this general principle? This is very easy to say, no? To develop this initial principle, to have some different idea from cadmium selenide. But then there are 2 points to be solved. First, what are small particles? What is the definition of these small particles? And once that we have prepared them, suppose that we know how to define and how to prepare them, how to process these particles for obtaining nanocrystals. So saying this general principle is easy. Implementing the principle could be extremely difficult or completely unrealistic. Rodolfo, how much time is left?
No, it's okay. You have 10 minutes more.
10 more?
Yes.
Sorry, I was going so slow. So, small particles. This is the preparation procedure for our indium oxide solution, the one that we have seen before and that we use for making thin films. What happens here? If we do not use any acetylacetone, if we just put the base, we have precipitation of indium hydroxide. We put the base inside the indium nitrate solution, we have a precipitation. This is a very basic experiment, of course. But in our procedure, we put acetylacetone around the molecules, just for avoid precipitation. And when we add the base, the ammonium hydroxide, for making the Sol-Gel process, there is no more precipitation. We go from a clearly white precipitate to a completely colorless solution. So, we define our small particles as those that are obtained when these condensation reaction that result in precipitation are limited, so resulting in a clear, transparent solution. So limiting condensation reaction, limiting the Sol-Gel process. What is the relationship with all the presentation that I've been doing before? Is that these procedures are the same that we develop for thin films. So once we have developed the principle, in the case of cadmium selenide, we could apply this principle because we had already defined our small particles. They are those which are generated when the Sol-Gel process is limited to obtain a solution without any precipitate. And we know how to do these particles. These are exactly the same processes that we have developed for thin films. This is why the first part was important. With the first part, we already know how to process, how to prepare these small particles. In the case of inorganic nitrates, we have the dissolution of our salt in methanol with acetylacetone, with the base, no precipitation. In the case of chloralkoxide, we just react our metal chlorides with methanol, in some cases plus acetylacetone. We add methanol. We don't have to do anything else. Adding the surfactant is related to the thin film deposition. I forgot to eliminate this part. So, from the first part, we know how to prepare, how to define these small particles. And then, how to go from these small particles to the nanocrystals. We need to condense these small particles in some way, because they are some kind of inorganic nanoclusters with a few atoms. I don't really know the exact structure of these nanoclusters. Then we have to provide some heating for having crystallization. But also, at the same time, we have to do in some way that these particles do not grow too much. At a certain point, the growth must stop, so we remain into the nanocrystalline regime. Otherwise, we have an enormous precipitate and we have not solved anything. So how to do this thing? Because we have two contradictory aims. We have to grow them in organic condensation catalysis. We have to do some Sol-Gel process to make these small particles grow a little bit more by condensing them. But at the same time, we want them to stop. We want their growth to stop at a certain point. How to do this? It is very easy. The procedure is extremely simple. We have our starting solution. These are the same that we prepare for thin films, exactly the same. We make a precipitate into an amine at room temperature, and then we make an heat treatment at 100 degrees C. This simple precipitation is at the same time making larger particles but stopping their growth, just due to the chemical properties and chemical structure of this dodecylamine that we're using in the synthesis. All those things that I was saying in the previous slides can be condensed into this step. Is our dodecylamine which is transparent at room temperature after being molten. We inject with the syringe the precursor inside. This is all. All those words are condensed in this simple procedure. Then we take this precipitate, we disperse it to oleic acid or into oleoylamine, depending on the system, and we make a solvothermal treatment. We need quite mild conditions, something like 220, 250 degrees C for 1-2 hours. Then extraction, purification, drying, blah, blah, blah. After all this processing, this is an example of the materials that it was possible to prepare. So we can explore a very broad range of materials, and we will see other examples in the afterwards. We have iron oxide in the oxide area, titanium. We can dope with palladium, with platinum. We can prepare metal sulfides, indium oxide, and many other materials that we can prepare by this general process that was developed by reasoning onto a strange case of cadmium selenide, and by using some precursors coming out from the work on thin fields. So putting everything together, we could prepare our metal oxide nanocrystals. What we do, because I remind that our aim was to prepare chemical sensing devices. So, this is our substrate. We make a suspension, we make a paste, we put some drops, we dry, and after a few steps, this is our final device. This is all. Everything is very easy. It's maybe terribly boring to explain all the steps and everything else, but making everything from the initial solution to nanocrystals to the device is so simple, so fast. And how do they work? This is the apparatus for the sensing test. This is the test chamber. We introduce various gases analyzed by multi-flow mass flow programmer, blah, blah, blah. And we can read how the electrical resistance change in presence of the gas, which is the response. This is the important thing. So, just a very clear example. This is a summary of the nitrogen dioxide sensing results with thin oxide nanocrystals. And we can see that with these materials, it was possible to obtain a response ranging over almost 3 orders of magnitude to as low as 100, for instance, ppb concentration of nanotube, which means that electrical conductance in these devices decreased by at least 1,000 times when exposed to such a low concentration as 100 ppb or even less than of nitrogen dioxide, which is a result which is not easily obtained with other oxides. So it was possible to prepare thin oxide nanocrystals, very tiny nanocrystals. They remained tiny even after the treatment, for reasons that I don't have the time to explain now. And the resulting devices were providing this enormous response to very low NO2 concentrations. I could show results concerning acetone sensing, ethanol sensing, ozone sensing with indium oxide. There are so many examples, but I don't want to show 10 slides with just the same figures. Just to say once again that we close the loop from the initial principle to the final device, but in this case, with respect to thin films, we were extremely more satisfied because the response that was obtained by our devices was enormous. Now to the final part of the talk. Do I still have some minutes left?
Yes. Yes, you have 5 minutes.
Okay, I will try to go as fast as I can. This is a recent topic that we are developing, which was suggested once again by some kind of curiosity of an observation suggested by curiosity, which catalysis, heterogeneous catalysis and gas sensors have many connection points. In the case of catalysis, we would like to obtain fast, selective, and efficient conversion of a given gaseous concentration that is carried out in proximity of the catalyst, by using minimum catalyst amount, of course. And we would like to convert the largest concentration of a known gas. For this reason, we need to amplify the extent of the surface chemical reactions. In gas sensors, we connect our catalyst to an external electrical circuit, but we still have many common points. We still would like to obtain fast, selective, and efficient conversion. Suppose you have to detect a toxic gas. It is very important that your sensor is very fast and very selective. We would like to use a minimum catalyst amount, a minimum amount of sensing material, because maybe we want to integrate our device into a more complex microelectronic architecture. And in this case, we would like to detect very, very small concentration of, in principle, an unknown gas. So what we need to do is to amplify the electrical effects of the surface chemical reaction. Here, the extent of the surface chemical reaction. We would like to go to the products as much as we can, as fast as we can, and so on. In the case of gas sensors, we would like that very, very small amounts of the products give rise to a very high electrical signal. So there is a cross connection between these two fields. And what is it suggesting? Suppose that we have some material like titanium, and we carry out a surface deposition of vanadium oxide. So supported vanadium is a very well-known catalyst. From this configuration, we can develop our gas sensing concept, which is answering to this question. May a surface layer of a more catalytically active oxide favor even the electronic exchange between the gaseous analyte and the sensing material? So the idea is that maybe the core material is quite lazy as a gas sensor, but then we put some layer of another oxide. This is very active. It makes the reaction very fast, very efficiently with the gaseous analyte, and the outcoming electrons are going to the core where they are transported throughout the device. It's, again, very, very nice to say, but it is necessary to see how to do, if it is possible to do, and if it works. But we know how to do the core. This is the case of titanium vanadium. This is the processing that I was showing before. Our solvothermal process precipitation dolicylamine, solvothermal processing, and so on. These are our titanium nanocrystals. And now, we would like to make some deposition of vanadium oxide onto the surface. How to do? Once again, we have already our substrate, our precursor of vanadium. It is a chloride oxide. Why? Because the core was prepared with a chloride oxide, so it is hoped that if we use a chloride oxide, the same class of precursor for the surface, for the shell, there will be much more chemical compatibility than if using another precursor, and we can effectively carry out this surface deposition. So how the synthesis works? Exactly as before, but before putting the vial with titanium precipitate into the autoclave, we add some chloride oxide of vanadium. Anything else? This is all. Then solvothermal processing, purification, and so on. The question is, have we achieved this surface cross-linking? Did we really deposit this vanadium layer onto the surface? And this is extremely difficult to be demonstrated. What we do was to carry out an enormous number of characterization techniques and to cross the results. And as a final result, it seemed that after heating at 400 degrees C, we had vanadium going into the structure of vanadase, but also occupying surface states. So this was an initial indirect evidence of the deposition that we obtained. Further evidence came from functional studies that I will be showing now. This is yields mapping of the materials, showing that the elements are evenly distributed in the sample. We have carried out this kind of analysis for many, many different samples, and in each case the vanadium distribution was always uniform, which is not always the case. For instance, this is another system, titanium modified with molybdenum oxide, titanium modified with tungsten oxide. We have our S-prepared materials, and after a treatment 400 degrees C, we have clearly a homogeneous distribution of molybdenum oxide. But if we increase the molybdenum or tungsten concentration, we clearly see that there are phase segregation inside the sample. So this work also requires a very careful control of the concentration of the other oxide and a continuous monitoring by characterization techniques of the results that are coming out. Very fast, some ethanol sensing, we could see that by adding vanadium, we had an increase of the response of the sensors by almost 100 times, almost orders of magnitude. So the initial concept, again, was satisfied, and it worked. It seemed that we deposited some vanadium onto the surface of vanities, and it works very well. And is it really working as a catalyst? It seems so. We see, for instance, that for two different ethanol concentration, we have pure titanium, and for increasing the response, it is slowly going up to 400 degrees C. We have to heat the device up to 400 degrees C. When we put vanadium onto the surface, we have exactly the reverse effect. We have the maximum response at high temperature, which is decreasing with increasing the temperature. So it seems that the vanadium introduction increases the response and decreases the operating temperature, which really seems the demonstration of some kind of catalytic effect. And I will stop here with gas sensors and these kind of applications. Why? Because it is interesting to show that a material that has been prepared for a given application may have some other interesting uses, some other interesting properties. For instance, with a colleague in Madrid, we were wondering whether this surface vanadium can modify the charge exchange of titanium, since vanadium has many different possible oxidation states with respect to titanium. And since he was working in the field of supercapacitors, the idea was to put together the good properties of these two materials. In which way? Because vanadium by itself is electrochemically active but has poor stability. Titanium has a good stability and on the other hand is electrochemically in many conditions quite inactive. So the idea was to take the good things of the two materials by using this kind of core shell configuration. This is the device preparation. These are the voltammetry curves of the pure materials, titanium and vanadium, and when we go to compare our titanium vanadium material with the pure titanium, we see that there is an enormous improvement of the properties. We have a wider potential window and higher gravimetric capacitance, which means that this small addition of vanadium onto the surface was capable of increasing enormously the capacitance of the material when working in the same condition of pure titanium. Once again, another application. We can couple our titanium vanadium nanocrystals with tungsten Oxide nanocrystals in a multi-layer configuration, where we can see that we can prepare an electrochromic device capable of separately operating over 4 different optical regimes, which is fully transparent, vis blocking, it is blocking the visible light, near infrared blocking, and it is completely able of completely blocking the both kind of radiations, which means that these coupling materials could be used in electrochromic windows for controlling the energy exchange of environments with the external atmosphere. And some results about water remediation with these multifunctional titanium vanadium nanocrystals and tin oxide vanadium oxide nanocrystals. We can also prepare other composition, of course. And we can easily see that there is a powerful water decontamination by supported vanadium with respect to methylene blue. Since when exposed to methylene blue into the dark, we see that the pure material go very rapidly to saturation, while the surface modified material can extract up to 80% of the initial methylene blue concentration in just 20 minutes, and after concluding the cycle, they can repeat it once again, while of course the pure material are completely saturated. This is, for me, it was important because it was a demonstration, an implicit demonstration that we really have some surface modification, some surface deposition. Because by electron microscopy, it is impossible to really see a vanadium shell. So in conclusion, we can start from the same precursor, and by chemical modulation, we can use it for making thin films, powders, pure nanocrystals, deposition onto titanium anatase core, tin oxide core, or whatever you do. Simply by starting from the same precursor and by using it in many other ways. This is also possible for the other precursor that we have seen before. Metal trophy hexanoids can be used for making nanocrystals, colloidal nanocrystals, not only thin films of powders. We can use precursors like those used for indium oxide thin films for making metal oxide powders from combustion synthesis. Or we can make the same synthesis than before, but if we do our solvothermal treatment into a sulfur source like dodecapire, we get this kind of, these are copper sulfide nanocrystals. So I would like to thank you for your attention. Thank you for your patience, since I believe I am gone much beyond the allowed time. Sorry about that. And thank you again, Rodolfo, for this possibility. And thank you.
Do you have any question? Mauro, in the case of titanium oxide, do you know what's the content of chloride? The final
and made XPS, and after the treatment it was eliminated. Yes.
Okay. And the surface area of the materials? You don't have
the pure material is something like 35-40 square meters per gram.
Okay.
When there is some vanadium deposition, the grain size is limited, so the surface area is increasing very much, up to 120, like that, something like that. It's much higher.
Okay. ¿Más preguntas? En español, inglés.
Have you performed any XPS analysis in order to see whether or not you deposit the vanadium oxide?
Yes. Yes, we carried out XPS, and there was clear presence of vanadium with the atomic concentration about 7% with respect to the titanium. And the oxidation state was always 5. After the treatment, it was completely oxidized. Mm-hmm. Yes.
Yeah, it was clear that vanadium was deposited.
Any other question?
About the sulfates, only you work with silica and
The substrate, silicon nitride.
only silicon nitride by a support?
Yes, silicon nitride or silicon oxide. The substrate is actually silicon, then they deposit some silicon nitride or silicon oxide onto silicon.
You never try to work with silicon, mesoporous silicon?
No. Maybe once in the past, but no, we didn't carry out that activity much in detail. No.
Thank you.
Okay. If you don't have more questions, let's thank again Mauro for